So as we know from last lecture, systems that support mechanical waves give rise to normal modes of oscillation. You can read in your text to see what normal modes of sound waves in wind instruments look like. I didn't feel like that was fundamental enough to cover in our fast-paced lectures here, but it is very interesting physics that goes on inside those windpipes of flutes and trumpets and all these other wind instruments. But to talk about resonance, let's use the example of pushing a child on a swing. So let's say that we have a swing set like this, right? And we have a little swing here, one lonely little swing that somebody can sit on. All right, so if we were to push a child on the swing, it takes a critically timed push during each cycle to get the child going anywhere. We know this if we tried. So this push would be called the driving force, which makes this type of oscillation a driven oscillation, right? So it's different from if you just start an oscillation off with some initial force or work or energy and let it go. Now we're adding something to it at a critical point in its phase each cycle. So that's a driven oscillation. If we push the child forward while they are on their way back towards us, which is adding negative work to the system, we certainly don't amplify their oscillation. We must start our push when they have ended their journey back towards us, and we must end our push no later than when they have ended their journey away from us. So we push them while they're going away from us, not while they're coming towards us. To pull this off, we have to time our pushes at the same frequency as their oscillation. No one push occurs for each swing cycle. If we accomplish this, we push the child higher and higher until they are happily swinging at full capacity. This system, with the oscillating swing and the well-timed push, is in resonance. In general, resonance is when an oscillating system is being driven at one of its normal modes, causing the oscillation amplitude to become much greater than the amplitudes of oscillation that the system commonly experiences. This phenomenon is exploited heavily in all areas of science involving light and matter interaction, from nanotechnology to lasers to microscopy and more things that I'm probably unaware of. So let me go back and revisit a sentence here that I said. So in general, resonance is when an oscillating system is being driven at one of its normal modes, causing the oscillation amplitude to become much greater than the amplitudes of oscillation that the system commonly experiences. So commonly experiences, so let's think about this swing. So sometimes there's going to be wind or maybe people running nearby causing some vibrations going on, or maybe a twig will fall from a tree and it'll hit it. And it'll cause some swinging or vibrations at the very least, but you don't see the swing swinging all the way up and down unless it's like a horror movie or something, or if somebody is pushing it at the right times, and that's why that is so such an interesting scene, and I forget what movie I'm thinking of, but they show that. But you're seeing the oscillation amplitude go much higher than it normally would by any random occurrence of in an ordinary system that isn't a swing. You might talk about thermal fluctuations, but in terms of a swing, we could talk about twigs hitting it. It's never going to swing all the way up just because a twig randomly hit it once, and you're never going to see a twig hit it, just the right way over and over and over. It's a very deliberate driving force that causes the swing to swing all the way up to its full amplitude, right? So that's what we're talking about in terms of a normal mode. It's oscillating at a normal mode when you're doing this. All right, so we already know what interference is from our waves on a string in the last lecture, but with sound wave interference, there's a phenomenon that arises due to interference that we commonly perceive, and that's called beats. And we're going to talk about what are beats and why we perceive them. So when two sound waves of different frequencies interfere, the sound that results is an addition of the amplitudes of each of the individual waves at a given time and space via the principle of superposition. So let's say you have a sound wave, which we will represent like this, and you have another sound wave that we'll represent like this. And if you can pretend that it's the exact same amplitude, right? Exact same amplitude here. And I know this is a transverse wave, but it gets the concept across a little bit better, I think. Right around here, if you add up whatever the displacement is, so what this y value is and what this y value is, you might have one of the highest additive waves that are the addition of these two waves. And then perhaps, let's look for another spot. Right around here, it looks like you would have the lowest, because this one's at its lowest and this one's also at its lowest. And everywhere in between, you get some other odd amplitude, which is some combination, right? Which is nothing like what I'm drawing, but, you know, it's some combination at every point. If you were to add what they are, it would add to some cumulative amplitude. So, since you can tell that it's a difficult concept to draw and communicate, as messy as that got as quickly as it did, I'm going to paste in something that I took the time to draw beforehand, I think. There we go. And we can talk about that. All right, so not as high quality, evidently, but we can still look at it. So you have a blue wave and a red wave, and they're a little bit out of phase. They have the same amplitude, but one's at a higher frequency than the other. So one of them is going up and down at a faster rate than the other one, but they're just slightly out of phase. And so sometimes, like where I've circled in here, and here, and here, they kind of are beginning to overlap. And then in the in-between times, they're pretty much like exactly out of phase. Like, well, maybe not there, but certainly there, out of phase. And so it would be more diminished in that region. And so if amplitude is intensity, right, and sound level that you're hearing, then what you end up hearing with a combination of just these two frequencies are these beat notes, where it's very quiet for a period of time, and then it builds, and then you hear this beat here, and then it's quiet for a time, and then you hear a beat, and then it's quiet, and then you hear, right? And the beats, you're only hearing beats because they're distinguished from the quiet parts. And that demonstrates, just with two frequencies, why we hear beats. And with more complex sound systems and more frequencies involved, and you get more complex sound. But that's the fundamental of why we hear beats. It's a series of soft, quiet, and then more intense loud at a regular interval that makes us hear beats. So, yeah. So maybe one example that comes to mind is if you open the back windows of a sedan in a car, and only the back windows, and you travel at some speed, then you hear this boo, 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 boo. It's not music or anything, but it is pressure, right? So you have this regular beat that's going on because of the fluid dynamics that go in the car, because the back windows are open. All right, one last.